This is a very ubiquitous physics problem. A mass, a block, a trunk in this case, sliding up or down an incline. This is a particular problem that we're going to need to learn to literally do backwards and forwards. All right, in this particular instance, we're pushing the trunk up the incline with a given applied force. All right, take note here that I'm not given the mass of the trunk or the crate or whatever we're sliding. All right, and this time I'm given the weight. How do I know? I look at the units. 325 Newton trunk. If they would have given me mass, it would have been in kilograms, and we'll have to multiply by 9.81. All right, but 325 is the weight. I do not fall into the trap of multiplying that weight by 9.81. If you divide by 9.81, you'll get the mass. Okay, so we're going to start this off by first analyzing the weight vector. And we've had an entire lesson on this. We want to take that weight vector and we want to break it into two components. All right, we learned that drawing this little imaginary box around our weight vector is a good idea. And then we can clearly see that we have a right triangle here that we can solve for the perpendicular and parallel components using the sine and the cosine function. All right, be careful. The side adjacent of this triangle is perpendicular to the plane of contact. So we use the cosine function there. We use the sine function to find the magnitude of the force that's parallel to the plane of contact. Okay, once we do this, our two-dimensional problem now becomes a one-dimensional problem. One dimension is parallel to the inclined plane. The other dimension is perpendicular to the inclined plane. So the weight vector of 325 is no longer useful to us. That guy is out. These components are in. Okay, so we're no longer going to work with the weight vector. We're just going to work with the parallel and perpendicular components. Okay, what are we going to do next? Well, that answers part A and B. What is the component of the trunk's weight parallel and perpendicular to the incline? Like I said, we've done a lot of problems like this, so we're pretty proficient in that. Now, C and D, the sum of all forces acting parallel to the incline and acting perpendicular to the incline. Well, we have a huge hint. This actually becomes a very easy question. F net parallel is equal to 0, and F net perpendicular is equal to 0. Why is F net perpendicular equal to 0? For the purposes of this course, we will always be perpendicular in one of our dimensions, and that will be the dimension that is perpendicular to the plane of contact. Now, how do I know F net parallel is 0? Because the problem states constant velocity, which means no acceleration. No acceleration by Newton's second law means the sum of all forces in that dimension must equal to 0. Okay, now the next problem, what about the friction force? How are we going to find that? Well, we do know a piece of information. We know that parallel to the plane of contact, we are in equilibrium. So all the forces acting parallel to the plane of contact must add up to 0. Let's take a look at them. We have 211, that's given, pushing up the plane. And then we have this parallel component of the weight of 111.2 newtons going down. And clearly I can see that these do not sum up to 0. So what do I need to do? I need to add in a force of friction that is also going to be going down the incline. And then I can solve, do a little bit of algebra, combine like terms, and solve for the force of friction. And I see that the force of friction must be 99.8 newtons down the plane. And this makes sense because if I'm pushing up the plane, the force of friction, sliding friction, is typically going to oppose my forward motion. So that means it's going to go down the plane. And then when we look, we have the 211 going up. We have the 111.2 going down, and we have the force of friction 99.8 going down, and indeed that now equals 0. All right, so that solves part E. Now let's get to part F. What is the kinetic coefficient of friction? Well, we have this formula right here, and this would make it very easy, except what is force normal? To get force normal, we have to look at our other dimension, perpendicular to the plane of contact. We must also be in equilibrium. If we look at the free body diagram, we are not. I need a force normal that is equal in magnitude and opposite direction of the perpendicular component of the weight. So force normal must also be 305.4 newtons. With that information, I can put it into my force of sliding friction formula and solve for mu k, 0.33. All right, now that we have that answered, now we're going to put quite a little bit of a twist on this problem. And now the trunk is going to reverse direction. It is going to slide down, and I am going to push upward to try to hold it back. Okay, now we got something unusual going on here. If I reverse direction, notice here in my free body diagram, look which way I put force of friction, reverse of what it was before. I am still going to be in equilibrium. So let's take a look at all of our forces now. Well, I know my force of friction, I've established that. I know my parallel component of gravity, I've established that. And now I need to look at my force applied. My force of friction is going up the incline. The parallel component of the force of gravity is going down the incline. I am still pushing up, but this time my force applied is my unknown. I do my algebra, and I need to have a force of 11.4 newtons up the incline in order to balance out the friction force in the parallel component of the weight. And that's how we solve this problem. Regardless of what variable you're solving for, this technique can be used on just about any problems. And it doesn't have to be constant velocity. I can take a look at my forces. If I have enough force information, I can find my F net. If I know the mass of my object, then I can get its acceleration.